She completed her PhD in 2018 from the University of New Hampshire, and her scientific interests are in the morphodynamic evolution and interaction of scales and natural and nature-based systems, with recent projects focused on beach and dune nearshore sediment transport, for which she's going to give us a talk today on. So the title of her talk is Beach Dune Subsurface Hydrodynamics and the Formation of Dune Scarps. I'm very much looking forward to your talk. So over to you, Meagan.
Well, thank you, Kristen. And yeah, thanks for having me. I don't think I'm on the coast to coast mailing list, but I'd like to be if that's a possibility.
You will be now.
Okay, thanks. Yeah, it's a really cool seminar series you guys are doing. So Kristen said the title of my talk is Beach Dunes Subsurface Hydrodynamics and the Formation of Dune Scarps. And this research was done with a lot of people, not just me. The universities are listed here. And on the last slide, I think almost everyone's names who came to participate in the experiments. But I'd like to give a lot of credit to my former master's student, Haley Bond, who did a lot of this work. And I'm presenting it, but she did a lot of the science too. Okay, so all over the world, we see dune scarps threatening infrastructure. I have examples here from the United States, but we see this in all different communities around the world. And once a dune or a beach scarp forms, it's really easy for it to propagate shorewards and put communities at risk. So that's the reason why we think about studying why these features form in the first place. And so the beach can go from, we have like examples from the tank here, but just like a mildly to steep sloping beach to dune interface, and then the scarp forms, and then we have scarp migration, where this process has been documented a lot in the past, where the waves come and impact the scarp. It gets wet. Oh man, something happened. Okay, it gets wet and then it slumps off. I don't know why it's doing, something happened to my, sorry about that. So it slumps off, and this has been documented by actually Rob Holman and Meg Palmston in the past, where the front of the scarp gets wet, it gets really heavy, and it falls off the slope. But what we don't really know is how or where on the beach profile these scarps will start to form. And in a lot of numerical models, process-based models, it's really just referenced to the steepness. So when your beach gets over steepened, then it will start to scarp, which has some truth to it, but there's a little bit more behind it. And that's what we're researching here. So in the wave lab, and I'll talk more about the wave lab in a few minutes, we looked at this process of how a beach or a dune goes from a smooth surface to a scarp. And we can see that it doesn't happen quickly. There's some perturbation that's formed, and then that perturbation eventually evolves into this scarp, and it's well documented that the slumping of the wet front sand can become a very highly erosive feature and propagate backwards really quickly if you have the right water level and wave conditions for that. So we did this experiment at Oregon State University in the Hinsdale Wave Research Lab. The flume, the large wave flume, is approximately 104 meters long. It's about 4 meters high and 3 meters wide. And we placed a bunch of sand, a whole dune in the flume. It was about 56 dump trucks plus of sand. And we placed it really strategically because we, in the past experiments, have kind of put a bunch of sand in the flume. We compacted it so that it would match the compaction of a natural dune. And then we tested 3 different dune archetypes. We tested a vegetated dune where we grew, you can kind of see the plants in the background. here we grew the plants in place in a greenhouse that we built over the Flume. We tested a bare dune, so just plain sand, and then we tested a bio-cemented dune where it was like looking at an engineering solution or potential solution for beach stability. I'm going to be focusing on the bare dune, but I do have some insights into the others if people have questions. So the wave conditions and water levels that we ran were mimicked from a hurricane, a scaled hurricane 1 to 2.5 scale. The dune was scaled in the same way. And so you can see the wave height, that was the hurricane in the green line, and then our modeled wave height in the wave lab as the yellow line. And then you can see the peak period in the next slide or plot, and the water level. So we were modeled surge by just filling the Flume at increments at a time in the far right plot. And the box in red is showing when the Scarp actually formed, and that will be the part of the storm that I was looking at. So during that storm, or that we were looking at mostly, so during that storm condition, the significant wave height ranged from like 0.9 to 0.95 meters, and the water levels were, this is with respect to our initial starting level. So the surge level was about 1/2 of a meter. So the research questions are, what are the physical mechanisms of Scarp formation? And then how can we think about parameterizing these mechanisms more efficiently in numerical models? So this is a really nice paper by Heiss 2020. And we got a lot out of thinking about this paper and the infiltration, the dynamics of this area where we go from fully saturated sediment to partially saturated sediment, and like a lens of unsaturated sediment. So when your swash bores, which is the gray line, runs up, the water infiltrates down through the beach, and it kind of creates this bulge of water within the beach. And we'll talk more about that later on. In Heiss's measurements, they were looking mostly at more like calm conditions, and we're taking this to storm conditions. Okay, so it's worth to review some, or maybe it might be new, some geotech terminology. So matrix suction is a force that holds partially saturated sands together. So this is kind of like when you build a sand castle on the beach. It's the force that is holding your sandcastle together. And it's all the little pore waters between the sediment has a little bit of water in it that kind of sticks the sand together due to capillary and surface tension. But when this force, when you get too much water, then you can actually, your sand grains will start to move apart, and that can trigger instabilities in the sediment. And that's when you might get momentary liquefaction or partial momentary liquefaction. So liquefaction itself, you can think of an earthquake, and this occurs when the effective stress in the sediment goes to 0. So that means that all of the sediment particles are like completely surrounded by a thin layer of water. So partial momentary liquefaction would mean that this partially happens. It's not complete liquefaction case, but it happens for just enough to destabilize the sediment. And then you often hear the term momentary liquefaction in wave conditions. So it's only like individual wave events that are causing liquefaction to occur, where liquefaction in the context of earthquakes, usually you don't hear it termed as momentary liquefaction. So that's where the partial and the momentary come from. Okay. Yeah, I guess I had this slide here. Yeah. So the wave passes by, you build up pressure in your sediment, and then as the pressure increases and the wave continues to pass by, then your sediment unloads. And during this unloading period, if your sand grains are completely surrounded by water, then you can have these liquefaction events due to upward seepage through your sediment. And that will make a little bit more sense when we look at data. Okay. So it is worth noting that if you're looking at the pressure gradient, DPE, which is the excess pore water pressure with respect to DZ, so that's your change in pressure over depth. If your pressure gradient is positive, then you'll have a stabilizing effect. So that will be like the water rushing down through the beach, and the sand grains will tend to stick together. And if you have a negative gradient, then that is destabilizing, and that becomes like quicksand. So then you have water rushing up through your sand grains and causing the sand grains to at that moment spread apart from each other and be much more vulnerable to eroding on the downrush of a wave. Okay, and so the critical threshold for full liquefaction is -1. And so anything, if you have your pressure gradient less than 0, so you can have positive pressure gradients, that would be stabilizing, and you can have negative pressure gradients, that's destabilizing. -1 would be complete liquefaction, but anything less than 0 can be somewhat destabilizing. Okay. So if you think of the force balance on a single grain, if your pressure gradient is less than 0 but greater than -1, then you can just have your sand grain be basically have the ability to be displaced in the context of making your matrix of sediment unstable. Okay, so liquefaction is one concept that we thought about a lot, and the other is slope stability, which is something that I think we all think about in the context of the beach. So you have a resisting slope, a resisting force on the bottom of your sand grain, and gravity is your driving force downwards. And if that is increased by downrush of the swash event, then you can have even more instability in your beach. Okay, so what we did was we instrumented the beach with a bunch of different sensors. We used moisture sensors that measured the water content and the water table in the beach, and those are in the blue squares as well as the brown dots. We had pressure sensors that we used to look at the water table elevation and pressure fluctuations, and those are the yellow triangles and the brown dots. So the brown dots were where the moisture and the pressure sensors were co-located. And we also had a lidar that was measuring each individual swash bore run-up on the beach, as well as the change in the beach elevation throughout the storm event. So we have a continuous time series of both of those two metrics. We had a bunch of other sensors, but I'm going to only be focusing on these. So I'm only going to mention those ones for now. So this is kind of an initial plot of the time series of what the erosion of our beach looked like. So if we just first focus on this inset plot, the color of the lines are trial numbers. So purple would be the first trial, and like the lightest yellow is the last trial. And the x-axis shows the tank coordinates, or the flume coordinates. So the wave maker would be like at x equals 0, and z is the vertical elevation. So we can see it, our initial profile had this berm in front of the dune, and then the dune is up over here. And then as we ran waves on the waves and increased the water level, we saw our beach erode back over time, and eventually the berm was eroded pretty quickly. So by trial 10, the berm was gone, and then we saw the scarp actually start to form around trial, we would say like the instability for it around trial 30, and then by trial 44, we had a full vertical face scarp here, and then it just propagated back in time. So the plot behind it is looking kind of at the same thing, but now, so you still have trial, or you have, but now instead of tank coordinates on the x-axis, you have trial numbers. So you have time on the x-axis and the flume coordinates or tank coordinates on the y-axis. So the wave maker is at x equals 0 again on the y-axis, and then the color is a time stack of the dune slope. So we actually see around trial 32 or so, this instability in the slope start to form. And then by the end, this would be these like really bright color yellows are the scarp. So it's a slope of 0.5, which is really steep. So we see this like steepening where the scarp starts to form around trial 32 or 33, and then it propagates back in time. This is a very similar plot, but now instead of as the slope plot, but now it's actually showing volume change per unit width, and it's a little bit complicated, so I'll walk you through it. Again, we have trial number on the x-axis and the flume coordinates on the y-axis. And now the color is, blues are showing erosion and reds are showing accretion. So if we ignore all the lines for a second and we just look at the colors, we see that when the scarp, so around trial 33, we see the scarp or the instability starts to form, and we have a lot more erosion offshore of where that perturbation begins. And then eventually we get a lot of volume change, a lot of erosion once the scarp is completely formed. This pink line is the scarp toe. So we could identify the scarp toe from maybe trial 34 on, and you can kind of see where it's located in the cross shore. But what's interesting, if we continue looking at the color, is this accretion color. So reds mean accretion, and we actually saw that onshore, starting from maybe trial 28 or so, onshore of where the perturbation and slope started to form, we see accretion of the beach face. And that's this really light red region here. And what happened was during the maximum run-up events, we observed that this has been documented by field studies as well, but during the maximum run-up events, we saw that the waves were actually depositing sediment on the top of the profile. So we were getting this juxtaposition of erosion offshore and accretion onshore, and that did eventually cause like a steepening effect that turned into this this full-fledged scarp. And so the brown dashed line is showing the maximum run-up event, and then we just have red, orange, and yellow showing different percentages of run-up events that reach that level. So this is just based out of literature determining our max, our 2%, our 10%, our 16%. So we see the scarp actually forming somewhere between the R 10% and the R 2% line. And the juxtaposition between erosion offshore of the scarp and accretion onshore of the scarp, we think was really important for the formation of that scarp. But we wanted to dive in a little bit more to why we saw such intense erosion offshore of the scarp. And now I'm going to reference this water table bulge a couple times in the next slide. So the water table bulge is this purple line, and you can kind of see, all I want you to take away right now is that we measured this with the pressure sensors, and you can kind of see that it follows, this erosion line, the line between erosion and accretion, pretty well until the scarp is completely formed. So this plot is showing the side view, the cross sections of the dune, again, with some different colors. So the trial 34 is blue and trial 41 is green. And then we have the location of the moisture and pressure sensors within the dune, where we were measuring different intra-sediment metrics, and those will come out on the next slides. And so the solid line here is showing, the solid lines are showing the cross section of the dune, where the dashed lines are showing the pressure head. So we actually see that the pressure head is building up somewhere around this meter mark 77. So we see this like bulge in the pressure head at meter mark 77. So that will be important. But the other important thing is if we look at the blue compared to the blue line, and then we keep going down through these trial numbers, we see that once we get to this like teal line in the middle, that the pressure head actually becomes higher in elevation than the sand surface. So what this means is that water is always at this point, on average, I guess, exfiltrating out of the dune because the pressure head is higher than the sand surface elevation. So I like to think of this as like an effective water table. I think traditionally the water table would be mostly underground, but you can have water tables intersecting with the ground, and you would have seepage out. And this effect is important. So you can see that from that teal line to the green line, we see the same thing and even more. So the difference between the dashed line and the solid line for the lighter green, the next lighter green is even more, and then even more for the last lighter green. So now we're going to look at a few different time series from the lidar and the pressure and moisture sensors that were buried in the beach. So the top plot here is showing the on the x-axis time, and on the y-axis is the cross-shore position again. And the dashed line, the orange dashed line here is showing the meter mark 77, where we had the co-located pressure and moisture sensors in the beach. So the top plot here is showing individual swash events as measured by the lidar. So we can see which events actually intersect or reach path beyond the this meter mark 77. And then the next plot down is showing the depth of water at this meter mark 77 for this swash event. So we can see like during this bigger event, we get more elevation of water at that location. And then the next plot is showing the moisture content from the 3 moisture sensors buried in the beach, and the color is also showing the volumetric moisture content. So the sensors M15, M2, and M14 are the stack right at meter mark 77. And then finally, the last plot is showing the potential momentary liquefaction. And we can see that during this trial 36, that at meter mark 77, we had mostly stabilizing events. So we didn't have really any of these swash events cause anything destabilizing. So they were like completely infiltrating through the dune. And if we look at this plot over here, we can see that the sand surface is this solid line, and the dashed line is that pressure head elevation, and the pressure head is lower than the sand surface at this trial. So if we go to the next slide, this is the same setup as before. Now this is trial 38, and we can see we have a few more swash events that are reaching past meter mark where we had all the sensors. And if we look at the plot on the right, we can now see that the elevation of the pressure head is higher than the sand surface elevation on average for this trial. And if we start looking at the moisture content, moisture M15 was the highest up moisture sensor. And during these bigger swash events, we see that the bore comes up, and what we interpret is that the water is kind of squeezed out, not really out, but a little bit out of the sediment under the weight of the bore. So the sand particles are squeezed closer together momentarily, and then during the down rush, so the bore is rushing down back to the ocean, or it's not a real ocean, but the fake ocean, you get these instability events. So you actually get the moisture content to like drastically increase at that moment. And we interpret this as like partial momentary liquefaction occurring. And we can confirm this with the pressure sensors. So we have high stabilizing pressure, and then when the swash bore rushes down, we get these dips in our pressure gradient that go below zero. So we have partial momentary liquefaction events occurring at each of these instances in time. And then trial 40, if we look at the little schematic on the right, we can see the sand surface in the solid line. And now the pressure head elevation is much above the sand surface. We have many more swash bores reaching past that meter mark 77. At this point, the moisture sensor 15 had eroded out of the dune, so we only have the next one down, moisture sensor 2, but we see the same like stabilizing and then destabilizing trend deeper down in the dune. And we have many more occurrences of partial momentary liquefaction. So if we look at this in time, so this is the entire time series from the start of trial 33. So it's not like from 0, it's just from 33. The top plot you've seen before, this is the slope of the dune. So we can see the scarp forming in this darker yellow colored line. And then each trial is partitioned by the solid or the dashed line. And we can see partial momentary liquefaction events occurring at each red highlighted color. So we can see many more starting to occur in time at that meter mark 77. So I'm going to come back to this plot in just one more slide, but I wanted to orient you to this metric that we were looking at, which is just the difference in the sand surface elevation, so the solid line, and the hydraulic pressure head, which is the dashed line. So I've been talking about that for a while. So if you see positive differences, that means it's stabilizing. The hydraulic pressure head or effective water table is below the sediment. And if you see negative numbers, then it's destabilizing, and the hydraulic pressure head is above the sediment. So effective water table above the sediment, water seeping out of the beach. And so now if we look back at this plot I just showed one slide ago, we can look at how this SSE minus HPH, so the sand surface elevation minus hydraulic pressure head on the x-axis, is changing by trial with respect to the depth of the swash bore running up on the beach. And then, so that's the y-axis, and then the color is the change in, basically the change in pressure over the change in depth. So that's the metric for liquefaction. So if it's a red color, a negative color, that means that we have partial momentary liquefaction occurring. And if it's blue, then that means that it's stabilizing. So if we look in time, we see that as the water surface elevation is moving closer to, as the sand surface and that effective water table are moving closer together, the same location would be 0, where the black line is. So if we march in time, we see that the water table is moving up in the beach. And then as that effective water table passes the elevation of the beach, we have seepage out of the beach. And that actually makes it much more vulnerable to these partial momentary liquefaction events, which destabilize the sediment. And then when the swashboard rushes down, carries a bunch of sand with it, causing erosion. So in conclusion, well, I have another extra slide at the end if we want to talk about it. But in conclusion, we observed the formation of a scarp. The water table bulge saturated the dune just offshore of the scarp formation location, and partial momentary liquefaction events occur after the peak swash events during drawdown. We also observed the strength of the partial momentary liquefaction events is related to swash depth combined with that effective water table elevation, and that partial momentary liquefaction events tend to occur when the measured interior dune total hydraulic pressure head is above that sand surface elevation. So the water is seeping out of the beach on average during that period of time. What we found as a big takeaway was that the slope discontinuity, which we do model in models like X Beach, actually forms due to this juxtaposition of over-steepening of the beach due to accretion from the maximum run-up events and erosion, probably from those same maximum run-up events, or not probably, but we observed it to be due to the same maximum run-up events, but causing partial momentary liquefaction during drawdown. So it was really the juxtaposition between accretion and erosion that caused oversteepening of the beach. And this initial slope discontinuity eventually did form into this full-fledged scarp. So if we can better estimate where the water table is in the beach, and look at that in context of the maximum run-up events, we might be able to better estimate when we would have a beach vulnerable to beach scarping or dune scarping. And eventually, once the perturbation became steep enough, then the scarp would form, and then slumping takes control, which we have a pretty good handle of, also called avalanching in some of the models. So these are all of the people that participated from all the different universities. It was a really great effort. The project was supported by the National Science Foundation in the US. And I have an extra slide of some ideas for modeling if we want to talk about that, but I guess I'll take questions, and then if people are interested, I'm happy to talk about some ideas. And this paper is, we're about to submit it, so it's not published yet, but it will be soon, we hope. Oh, I could continue sharing.